Now we're going to deal with head loss in the pipe. And actually we're going to start putting together some formulas so we can calculate out the head loss and feed it back into our energy equation. So let's start by looking at a situation. And I'm going to look at this angled pipe here. And so this is what I'm going to be using for this discussion. A couple things to note is right here we have a fully developed flow profile. We're just going to assume that we're beyond the entrance length. And what you see over here, this is a shear stress profile. Notice the shear stress as we get to the wall is the largest, which should make sense. As this profile is coming in, the middle stays in its inviscid core the longest, so we should get the minimum amount of stress along the center line of our pipe. And let's take a look at it. And looking at this pipe, diameter of 1 is equal to the diameter of 2. It's the same radius, it's a constant temperature pipe. Excuse me, constant diameter pipe. So that tells us that Q1 is equal to Q2. Since the areas are the same, that tells us the velocity at 1 is going to be equal to the velocity at 2. So, makes sense. The velocity shouldn't be changing because the pipe diameter isn't changing. We're going to make a couple of assumptions on this, and we're going to assume a steady, incompressible flow. Steady because I just don't want to deal with those time derivatives. Incompressible because we're just using a fluid or a very slow-moving gas. Now, we're also going to assume that there's a streamline that goes from here to here, but we're not going to assume an inviscid flow. So we can't use Bernoulli's equation. And the reason I don't want to assume is an inviscid flow is HF is going to be how much loss we have due to friction. So if I assume that the pipe is inviscid, what I'm going to end up happening is I'm going to have no frictional losses in the pipe. So now if I write Bernoulli's equation between point 1 and point 2, as I said, I can't use Bernoulli's equation because that's one of the 3 assumptions that I made to get to where we're at. So what we're going to do is when we remove that assumption, since we did not work out the math, we're going to be at a different equation, sort of a modified version of the Bernoulli's equation. So what we're going to have is pressure over gamma plus alpha. That's my Greek, that's a lowercase Greek little alpha. We do not want to neglect your classical Greek education in this class. V squared over 2g plus z, and this is all at point 1, and that's going to have to equal pressure over gamma plus alpha v squared over 2g plus z at point 2 plus whatever frictional losses that we have between there. Now I just realized that I did not explain what alpha is, but that's okay, we'll do that now. Alpha is what's called a kinetic energy correlation factor, or kinetic correlation factor. Now this is to adjust the equation for the difference in laminar or turbulent flow. Now in laminar flow, alpha is typically set to 2 for laminar flow. For turbulent flow, alpha is pretty close to 1. It's usually a little bit over. You will see problems where they sit there and they adjust alpha just a little bit to tweak it around. It's they measure it. There's a way to calculate it out, but that's beyond what we're going to do in this class. So what we are going to do is we are assuming that we're in the fully developed region. So let's actually put that in our assumptions. So fully developed. So we're far enough away from the entrance that it's not going to affect anything. And if that's the case, well then I know that alpha will be the same because we're fully developed. I also know that v squared is going to be the same because v1 has to equal v at 2. And so since we've got this additive equation here, we can sit there and go, okay, well, those velocity terms are going to fall out. And so what we're going to be left with is the equation for h sub f is just going to end up reducing down to the change in height and the change in pressure. So HF is going to be Z1 minus Z2, so there's our elevation change, plus P1 over gamma minus P2 over gamma, which we can rewrite as just saying, okay, well, that's delta Z plus delta P over gamma. So the head loss, the way that we would find it, is going to be the change in height, or the change of the gravity head, and then the change of the pressure head. And I'm going to mark this equation with a 1, because we're going to come back and use this equation for something else. Let's look at this in a slightly different way. So instead of looking at it in the context of Bernoulli's equation, why don't we do a momentum balance from point 1 to point 2? So we draw our control volume. We're going to do our momentum balance from 1 to 2. So we're going to look at all the forces along the x direction. And so what forces are those going to be? We have pressure forces that are moving it. We have shear stress forces. Those are our frictional forces at the wall. And we have gravity forces. So if I look at all of these forces in the context of conservation of linear momentum, so the sum of the forces in the x direction, which the x direction is along the pipe length, what are we going to have? Well, if I look at the pressure that's acting on this side of the pipe here that's pushing on, well, what's that going to be? Well, that's going to be the pressure at 1 going in the positive direction times the area. So pi r squared. Now on the other side I have the pressure acting in the other direction, so that's minus the pressure at 2 pi r squared. And so now we look at the gravity forces. So gravity, we can see we've actually already figured things out. So if the gravity force is going to be acting along the x direction, so that's going to be G sine theta. Well, then we also need how much this whole thing weighs. Excuse me, how much mass is there? And so we are going to take the density, and then we're going to multiply it by the volume to get the mass. And so the volume of this is going to be the volume of the cylinder, which is pi r squared times the length of the cylinder, and then times G. So, but G along the x direction, so G sine phi. And that's a positive, because that's acting in the positive direction. Last thing we have is the shear stress. So tau sub W for shear stress at the wall, and that's going to act across the entire outside surface of our cylinder. So the surface is going to be 2 pi r, which gets us our circumference, times the length, which gets us the entire surface area. And all that's going to equal is the momentum of the fluid, so the sum of all the m dot v outs minus the sum of all the m dot v ins. Now we've already stated that v1 is equal to v2, which also means the mass flow rate at 1 and mass flow rate at 2 are all constant. That's going to end up being 0. So if I rearrange this now, I've got my sum of my forces are going to be, we've got P1 minus P2 times pi r squared, just to simplify things just a little bit. And then we have L, the L in the sine theta, excuse me, L in the sine V, not V, phi, so PHI. What is that going to be? Well, that's going to be the change in height from here to here. This is, right here is going to be L sine phi. I just want to call that delta Z, because that's my change in my height. And so what that leaves me with is rho G pi r squared. And now I'm going to subtract from that my shear stress at the wall, which is going to be 2 pi r times L. And then finally I'm left with everything on the other side, which is 0. Now I want to take this equation and rearrange it a little bit to be in the same term, the same forms as our equation that we did using Bernoulli's equation. So what I'm going to do is I'm going to take I'm going to take this P1 minus P2. I'm just going to call that the change in pressure. I'm going to divide through all three terms by pi r, and that will leave us that. And then I want to isolate the delta P and the delta Z on one side, so I'm going to end up dividing through by r and also gamma through all three terms. And so once I do that, what I'm going to be left with is on this side, I'm going to have delta P divided by rho times G is gamma plus delta Z. So now that looks exactly like equation 1 did. And then what I'm going to be left with on this other side is going to be 2 times the shear stress at the wall divided by gamma times L, the length of our pipe, divided by the radius. Well, we can also, if we want to use the diameter of the pipe, you can multiply through by that, and that's fine. So now, if I take a look at that and compare it back to my other equation, so let's roll this back to back in the notes a little bit. And see here we got delta Z is equal, plus delta P over gamma is equal to HF. And so I have delta P over gamma plus delta Z is equal to this, and this is also equal to HF. So now we have an equation where we do not need the pressure and the gravity drop to calculate HF. Now the one thing to note with this equation is that HF now we can calculate knowing the shear stress at the wall and some other easy properties. Now, the one problem that we have is calculating the shear stress at the wall. A fluid, a liquid, or a gas, we can't really attach a strain gauge to and measure how much shear stress is in the fluid at that point. So we're still going to have to do some stuff, and we're going to have to kind of back work in what the shear stress of the wall is, since we can't directly measure it. We need to get it in terms of things that we can measure. Now we can measure the H of F looking at the pressure drop and the height drop, but that's not going to help us in a lot of the things that we're trying to do and trying to predict, because a lot of times we're going to be trying to predict what pressure is given things, but there's other ways to do it. And we'll continue this. There's a part 2 of this where we'll talk about the rest of HF.